Welcome to Advanced Operating Systems. This is, I think, the 20th time I'm running this course. No, 25th time. We started in '97. It evolved over the years, but it's fundamentally still been the same. It's meant to be a fairly intense course for people who really want to dig deep and get their hands really dirty and build real stuff and really on the side learn about operating systems. So, by the way, my slides are under Creative Commons because they'll get ripped off anyway, and so I decided to just put them out there, hoping people will at least acknowledge that they ripped them off. So, why do we do advanced operating system? Why am I teaching advanced operating system? And why am I excited for you to want to learn advanced operating systems? It's some of the answers that have been given here already. Understand operating systems in depth. Understand more about operating systems design. Inherently, that's a bit narrow. I can't tell you everything about how to design any operating system, so we're specifically focusing on microkernels and microkernel-based operating systems for pretty good reasons. Also, how to actually design and build a large-ish system on your own. For most people, other than the thesis, this is the biggest piece of software they're going to write at uni. It's a challenging project you're going to do, and that's design. We want it to be challenging. One of my rules is it's a crime to under-challenge smart students, and students who get here are generally pretty smart, and so it's my job to challenge them. And also, just dealing with the complexity of real-world systems, and particularly operating systems have a high amount of conceptual complexity. And so that's what we call the systems experience. Systems code is inherently difficult and complex. And so learning to design an operating system pretty much on your own with a lot of guidance. We do give you a lot of guidance. As you might have noticed, if you looked at the project, we'll give you almost weekly milestones with clear deliverables, so that you can actually learn how to, that you don't run off on a tangent. And we have a set of very experienced, excellent demonstrators here. Some of them are here. I spot, can you guys just stand up? So this is Mitch, that's James, Ivan, and Andy. That's about half of them. We have 6 or 7 in total. Hopefully the rest will come later and I can introduce them as well. There's also Lucy, and there's Courtney, and there is Jack, and that's it, I think. You can sit down. You can also leave if you like. Also, so all of our demonstrators have done the course themselves last year and done pretty well. And almost all of them are now in my lab in the Trustworthy Systems group helping me to change the world. And you can do the same. So this is building a real system with guidance from experienced tutors that look at your code, look at your design, make sure you have something that will scale up throughout the term. And obviously, as I said, I want to challenge students, so tackle a real challenge. And also, later in the course, I'll be covering research topics, mostly related to what we do, microkernels. And all up, you learn a lot of skills that are very useful obviously in operating systems research. The course has been a feeder for my research pipeline for a long time, but also extremely sought after in industry, like the likes of Apple, Facebook, Qualcomm, Google, bunch of other high-tech companies. They love to hire the skills we produce here in advanced operating systems. So they're very useful both for industry as well as for research. But then, very importantly, I want you to have fun. And this is why we have relatively strict entry barriers into the course, and also ask you to drop if you struggle on the first two milestones, because if you struggle on those, then chances are you won't survive it, and that's why we do that. So we have a relatively fast start. Once you're over that hurdle, we're fairly confident you'll make it. And I haven't failed anyone in many years, anyone who made it past those initial milestones. So that's it. You're expected to work hard, but I definitely hope you'll have fun doing it. Specifically, in today's lecture, I'll give you what I call a whirlwind introduction to microkernels and seL4, because I want you to throw at you all the material you need to do the project this week, so today and on Thursday. And that means necessarily it's fairly condensed. And I gloss over a lot of detail, a lot of the reasoning behind things, etc. Just sort of give you, after the basic introduction to the principles, a relatively quick rundown on how seL4 operates or how to use seL4. And then you should be ready to get started with the project, and then we can sort of dig in later into more details. So today, general microkernel introduction, seL4 principles, and then start on the seL4 mechanisms, particularly IPC and notifications, the synchronization mechanism, and then the rest will be covered on Thursday. And then after Thursday, you should be able to start on the project, and it basically starts then, and the first milestone series due on Monday, I think, right? Cool. Any questions up to this point? Nope. Good. So let's have a look at microkernels. What are microkernels? You've seen a microkernel of sorts in the basic OS course. OS 161 is a microkernel, not sort of in the strict sense as seL4 is, but it gives you the feeling it basically doesn't have a lot of useful functionality that's all built on top. So microkernel is in contrast to what's called a monolithic kernel. So monolithic is where most of the operating system functionality is in the kernel. And the kernel, by definition, is the software that executes in the privileged mode of the hardware. So in a system like Linux or Windows or Mac OS, you have almost all the system services inside the kernel, in particular file system, networking, virtual memory, and all that stuff. And in terms of file systems, there's multiple layers of abstractions. So basically, it's a vertically layered system where there's a lot of internal abstractions that build on each other until you get presented with the actual system call interface. And in contrast, the microkernel is a horizontally structured system. It has this thin kernel with just very minimal functionality, and I go into a bit more detail on what that means. And everything else is built on top as user-level programs. And from the microkernel's point of view, there's no difference between a system service and an application. It's just a process running in its own address space. And importantly, all these components, including various OS components, they're encapsulated in their address space. What's the advantage of doing that? And the whole point of this approach? Security. Yeah, security is one aspect. In general, sort of robustness is the general term. Basically, if something falls over, there's an encapsulation of the fault containment, right? And of course, that has strong security implications. It was not initially done for security, but these days, that's the real driver. That's why we use it for seL4. Yeah, faults get contained, and the system has a chance of surviving a fault in a component. And in particular, with respect to security, that means if an attacker compromises one thing, for example, one of the, I don't know how many file systems, Linux, I think, supports something like literally dozens of file systems, hundreds or thousands of device drivers, etc. Each one, if compromised, will compromise the whole system. In a microkernel, if other functionality is not dependent on the compromised component, the system can keep operating. And in particular, it's much harder to attack because you can only attack a particular component at the time, and therefore it's much harder to compromise the whole system. Unless you manage to compromise the kernel itself, of course. And this is where we have a real difference, where in the monolithic system, oops, where do I was jumping ahead of myself. This is this slide. In the monolithic system, you have order of tens of millions of lines of code in the kernel. Whereas in the microkernel, a well-designed microkernel like seL4, you got 10,000. And general rule of thumb, software engineering is you have 1 to 5 bugs per line, per 1,000 lines of code. So that means the bugs in the microkernel, the expected number of bugs you can count on your fingers, whereas in the Linux or Windows case, there's literally thousands, if not tens of thousands of bugs there, and that's why they get compromised all the time, right? So that's the basic idea. So the idea is that, yes, you have a system that's inherently more robust. It's also easier to adapt because if you want to support a new file system, then that's just another process running as a server on your microkernel. You don't have to mess with the rest of the system unlike Linux. So you can easily add features. The kernel interface can remain stable, etc. So ideally, it's more adaptable, more dependable, and easier to optimize because you just have to optimize 10,000 lines of code, right? And all the user level services, they can all be optimized in isolation. So that's the basic idea. The idea goes back to 1970, believe it or not. It's almost as old-fashioned as virtualization, even though many people think virtualization was invented 20 years ago. It's actually even older than microkernels, but it's a very old idea, so it's more than half a century old, even older than me. And it's been sort of not too popular for a long time until in the last decade or two when microkernels have really sort of, where people really started understanding why this is a really good idea to design systems that way. And security has a lot to do with it. So what defines a microkernel? There's various ways you can define it. I like the one by Jochen Liedtke, who built the world's really first fast microkernel, what he called L4 at the time. And that's the reason why seL4 is called seL4, because it's a descendant of this L4 microkernel from Jochen Liedtke. And he defined microkernels through the minimality principle. A microkernel contains only the code that needs to run in kernel mode in order to be able to deliver the required functionality. And if you think of that, that's not a lot, right? You don't need file systems in the kernel. You don't need device drivers in the kernel, with the exception of a interrupt controller driver. That's about the only device, and a timer driver for preemption. That's the only drivers you need in the kernel. And beyond that, as we'll see, the kernel is mostly a fast context switching engine. Its job is there to just multiplex the hardware and then securely switch it. So that gives you a small trusted computing base it allows you to design a system with a small trusted computing base, because any code that runs privileged has to be trusted, because there is no protection from any kernel code. It can execute whatever it wants. It can do to hardware whatever it wants. So it necessarily is trusted, and that means it's the core of what's called a trusted computing base. So in a system like Windows, you have tens of millions of lines in the trusted computing base, which is, of course, impossible to get right. So that reduces the attack surface, but the flip side of the coin is it's much harder to properly design microkernel-based systems so they actually perform. And that has been pretty much what's been holding back microkernels for decades, until Jochen in 95-ish came up with the seL4 kernel that showed that you can actually do these things fast. And since then, we have learned how to structure systems on top of microkernels to get performance. And one of the projects I have at the moment. Lucy is doing that, who is one of the demonstrators. She'll hopefully show her face, is to actually demonstrate we can do I/O networking, gigabit networking on seL4 as fast as on Linux, even though we have extra context switches when we switch between the driver and its clients, etc. So because of this design in the microkernel, where you have system services provided by servers running at user level, an application can't just do a system call to obtain a service as in Linux, right? It has to do a context switch to the server, and that's it's enabled by the kernel-provided IPC mechanism. It's actually not quite as bad as it sounds. Obviously, this extra context switch is pure overhead in a way. That's sort of what you pay for security. But I can show you that the overhead is actually really, really small if you do it right. Certainly tiny compared to the cost of the typical system call. But also, these systems, the vertical layering also introduces overhead. If you think about what happens if you do a file system call, for example, in Linux, you trap into the kernel, then there is a low-level handler that figures out what to do, and it finds it's a file system call, so it goes up to the VFS layer, and that decides which file system it goes down. So it crosses a lot of internal boundaries, and all these abstractions, they add up as well. So the cost issue is not quite as obvious as it might seem at first. But inherently, there is a cost. Okay, so this is, in a nutshell, the philosophy of microkernels. And in terms of where seL4 sits, the microkernel we designed, implemented, and verified, it's sort of at the end of a family tree that goes back about 30 years. It's not quite as messy as the family tree of Linux, but or of Unix, but it's there's quite a few out there. So the original one was L4, Jochen's first really high-performance microkernel, which was a successor of L3. He wasn't very imaginative with his names. L3. He had two other systems before. So one was called Eumel, and the other was a compiler for a language called Elan. And then we ran out of good names and called it L3 for Liedtke's third systems, and then there was L4. You could say seL4 is L5 in a way because it's really a new generation, but we call it seL4. So that happened in the mid-90s, and then we got into that game. Everything in blue here is done here at UNSW, and the light blue stuff is a startup company I founded 12 years ago. Yeah, no, 16 years ago. And so you see that there's a bunch of other kernels out here. You hear these names every now and then. Pygos is a commercial clone of an early version that's flying in aircraft, etc. And then there was L4 embedded, where we took a fork of a then latest kernel, optimized it for embedded systems that are resource constrained. It went into phones. Phones were extremely resource constrained in those days. They're no longer. Then there was this OKL4 microkernel, which was the first product of my company, Open Kernel Labs. That was the first one that had capability protection. And it also went into Qualcomm modem chips. So that's, if you like, was the first real commercial success when Qualcomm shipped L4 on all their modems from about 2006. And an actual earlier version, then about 5 or 10 years after Qualcomm went into the secure enclave of all recent iOS devices. So if anyone has an iPhone or an iPad or anything, one of our L4 systems is running there on the secure enclave. So the coprocessor that does all the key management and fingerprinting and etc. And then there's seL4. The various errors show either API inheritance or code inheritance, and you can see seL4 has neither. It was done completely from scratch, a new design, new implementation. And that's what we're going to talk about. Any questions up to this point?
Do the L4, seL4 stuff, do they have any, because I'm vaguely aware of things like POSIX and GNU, standardizing things. Do they have any similarities or any bookends to that sort of system?
That's a really good question. And the answer is that these various L4 kernels, they have a lot in common in terms of the philosophy, some of the design, and some of the sort of abstractions they present, but there's no attempt to actually standardize them. And that's for good reason, because in a microkernel, it's like the most performance critical bit in the whole system, and you really need to optimize the hell out of it. And any sort of attempt to provide a standardized API or so costs you performance. And these systems, even seL4 is still developing. We first released it in 2009, so that's 13 years ago. As a matter of fact, we'll have seL4 Day coming up in a few weeks, which is the 13th anniversary of completing the verification of seL4 and the 8th anniversary of open sourcing it. But we keep evolving the kernel. Mostly, and I'll talk about that in more detail later, but mostly we're trying to address broader classes of use cases. It's meant to be a general purpose system. Doesn't mean it serves all application domains equally. And so we're working on really, we're fine-tuning the API, if you like, and that's continuous. So yeah, I'll talk more about that later. Yeah?
Sorry, what does L4 actually, the name, what does it stand for, the L?
L4 was the success of L3, and L3 was Liedtke's third system. Okay, any other questions?
Yeah, there's been 9 years since the end of that scale. Has anything interesting happened? Well,
there's no new, what I would call L4 kernel since. Why would you bother? You have seL4, right? In a way, we sort of removed the incentive to develop a new system from scratch, because catching up just with the verification story of seL4 is a pretty big challenge, and it's open source, so why bother? All right, so let's look at seL4 in more detail. It's built on a number of principles, very few exact, actually. One, of course, is the fundamental underlying principle, the minimality principle, which in some ways seL4 is probably closer to the ideal than any of the previous kernels, but it's not. There's some things in the kernel which could theoretically be done at user level, in particular scheduling, but it's in the kernel for good reasons. And again, I'll talk about that later, probably in the real-time lecture. So besides this underlying minimality principle, we have the core mechanism for protection, the core authorization mechanism is capabilities. Who's heard of capabilities in the OS context before? Yeah, Scotty doesn't count. He's my postdoc and working on one of the verification projects, which I'll talk later about. There's an explanation about capabilities coming up, but for now it's an access control mechanism, and it's the only one in seL4. And recently we extended that to time, so we now have a common way of authorizing any resource use in the kernel, including time. And the other is all resource management is done at user level. So the idea of policy mechanism separation is very old and sort of very natural in the microkernel concept, that but if you minimize things, you really need to reduce it to fundamental mechanisms. And any policy sort of gives you additional complexity, but also restricts what you can do. So if you think a standard system policy, can someone think of one you might have in Linux or so? For example, file systems. If you access blocks on a disk, any policy that comes to mind? LRU is one policy, yes. Let's pick that one. That's used, for example, for memory management, right, paging. That is a really good case because it represents the fact that policies tend to serve maybe 90% of use cases pretty well and can end up pretty appallingly bad on the others. So in the LRU case, it generally works fairly well, except if you have a working set that's just a bit bigger than your physical memory and you have sequential access. Then LRU means you always throw out the block you're going to need next. So it's really the worst possible policy. And that's typical for policies, right? They're designed for, they're a bit like heuristics, if you like. They're designed to serve a large class of use cases well. It's probably not perfect for any of them, or at least not for very many. And then there's always some that are outside, which are really poorly served. And if you bake the policy in the kernel, then you need to change the kernel to change the policy. And that's a bad thing for a microkernel, which you want to keep stable, and in particular when you verify it. And of course, it's even worse putting policies into hardware. And I would love that more architects would understand that. Computer architects, particularly at Intel, love to put policies into hardware, and that's really a bad thing because once it's in hardware, it's so hard to change, right? So don't do that. Put it in user level, and seL4 takes that to extreme. And that really treaded new territory in that, and you'll have fun with this because it gives you a huge foot gun. And we sort of diffused the gun a little, giving you some libraries to manage that. But if you were playing with really naked seL4, then the fact that you have to do all your resource management at user level is extremely difficult to manage. But it's a very powerful concept. So that's why I say it's painful to use, but it is one of the key things that allow us to reason about security formally in a seL4-based system. And because it's such a huge gun to aim at your foot, we provide you libraries that hide a lot of this complex resource management so you can go on with the design of your system, which is generally a good idea, right? Have an abstraction that's sort of good enough for what you want to do, and then once you've done the design, you can rethink the abstraction if you want. And really key, that was the drive of seL4 from the beginning, and has influenced its design as well as its implementation, is that we wanted to prove the thing correct. So the idea is we have this really small microkernels, 10,000 lines of code, so by the rule of thumb, maybe only 20 or 50 bugs in there. Can we completely eliminate them? And obviously, by testing and code inspection, you may or you may not. You just don't know. Whereas the only way you can know is by mathematical proof, and this is what we pioneered with seL4. It was the world's first operating system with such a correctness proof. And I'll talk about that at length later in the term. So that's what we finished 13 years ago. Yep. And if you want to get more ideas of sort of the thinking that went into seL4, I've got a blog written up about that. Feel free to have a look. So these are the principles. And now what are the concepts? They are also called abstractions, I guess. And there are few enough in seL4 that I can fit them into a single slide. That's a bit overloaded, but it's not too bad. So there's really two categories of concepts. One is capabilities, which I mentioned before. So they are the protected references to kernel objects, and I'll explain that in a minute. And then there is 10 types of kernel objects, and that's it. What are they? There's threads, which is the abstraction for execution. So a thread is represented by a thread control block, and that contains basically the thread state. And by controlling thread control blocks, you can control threads. And you can assign threads to a CPU. The second one is scheduling context, and that's the abstraction for managing the time resource. A scheduling context, if you like, and again, I'll get to that into more detail, is the right to use the CPU for a limited amount of time, or rather a time share of the CPU. So it's the core mechanism for managing time as the time resource. And then there is address spaces, therefore virtual memory, right? And seL4 address space, the seL4 address space abstraction is just a very thin wrapper around hardware page tables. And it's so thin that it's not even ISA agnostic. So the page table, the address space abstraction is actually architecture specific. It looks different on different architectures because it's just a minimum abstraction around hardware page tables. Again, this is intentional to remove policy because the user level should be able to do with the hardware anything any software can do with the hardware within the security limits enforced by the kernel. And then there's endpoints, and these are the fundamental abstraction for communication in the system. So address spaces provide you isolation, spatial isolation. Scheduling contexts provide you temporal isolation. And if you have only isolation, then you can't build interesting systems. You need communication as well, and that's provided by endpoints. Then there's reply objects, which are special kind of endpoints, which I'll explain in a minute, basically to support client-server interactions. Notifications, which is the basic abstraction for synchronizations, so they're like semaphores. Capability spaces, they are representation of protection domains, so they define the access right of a process. And an access right in seL4 is a collection of capabilities, so they're basically data structures that hold capabilities. And then there's frames. They represent physical memory, so frames of things you can map into address spaces. And then there is some architecture-dependent stuff for dealing with interrupts. So they are interrupt objects, and how they look like is very much dependent on what the ISA offers in this. And then the final one is untyped memory, which is basically free memory. Memory that has not been, physical memory that has not been put to any particular use, and that can be retyped in any of these other objects. That's how you make use of it. And that's it. And there's logically only 3 system calls. If you know anything about capability, you should ask, why do I need more than one? Because in the capability system, all you do is invoke capabilities. It's a little bit more complicated, but basically there is 2 ways to communicate by invoking objects. And they're named after the model for communication. So call is invoking a server, and reply receive is the server. And the same system calls get also used for invoking any other kernel object. For example, operating on a thread means invoking a thread capability, etc. And then the special one is yield, which just means give up your time slice. And that's an unclean one because it's not authorized by capability. I haven't got a clean way to do that yet. Okay, so this is really all the concepts you need to understand seL4. Doesn't sound like a lot, right? Turns out there's a fair bit complexity behind that. Completely understanding seL4 is definitely not a trivial thing, but it's fairly bounded. You can imagine that you can actually understand all that, right? The whole manual is, I don't know, 100 pages or something, which is very fluffy. Things that are not the seL4 concept, specifically hardware abstraction. I mentioned that before because abstracting hardware introduces policy and violates minimality. So we specifically do not try to abstract over hardware. And as a true microkernel, the mechanisms are just thin wrappers around hardware mechanisms. A microkernel has also been called a CPU driver. I really like this term. It's been invented by one of my students and then got into a paper by people from ETH Zurich. We did a different kind of microkernel system. And there's also similarities to exokernels, which I may or may not talk about in the lecture. So these are the basic concepts. You should have a feel for all of them, except capabilities, probably. So what the hell are capabilities? I already said capabilities are the basic way we deal with we represent access rights in an seL4 system. They're not an invention of seL4. Capabilities also go back to the 70s, like just about anything in computer science. Everything was invented in either in the 70s or in the 60s. And then many things got forgotten, and some for good reasons and others not. Capabilities was one of them that almost got forgotten until they got dug out again in the 90s, and they're really powerful. So the basic idea of a capability, it's an access token. So you can always think of a capability as a key. An object has sort of a lock because it's protected, and in order to access it, you need the right key for the lock. That's your capability. And more concretely speaking, a capability really encapsulates two things. One is an object reference, and the other is access rights. And that is enough to control access. Basically, in a capability-based system, any operation is an invocation of a capability. And that's how things work in seL4. So that's why we only have 2 or 3 system calls, because it's really the capabilities that say what you want to do. You invoke a method on a capability. So the capability implies the object it's referencing. It doesn't tell you that. You can't see that, but the kernel knows. The kernel from the capability finds the object, and it also encapsulates what access rights you have to that object. So if you think of an object like a file, then you can have object references, file references that imply the right, whether you're allowed to read or write to the file. Does that sound familiar at all? It should. Where have you seen that before? Well, mode bits are access rights, yes, but there's something you should be quite familiar with, which is actually capabilities. Even people don't call them that. Ever heard of Unix file descriptors? They're capabilities because they're exactly that. They reference a particular file and imply access rights. How do file descriptors work? Yep.
And then that leads to like the right file.
Yes. So in a nutshell, when you open a file in Unix systems, files are represented by inodes. They contain the pointers to the actual data, etc., and metadata like the mode mask. So when you do an open of a file in Linux, the system looks up the path name, right? Finds the inode, caches it in memory, sets up a file descriptor that points to the inode, and contains the access rights with which you opened the file. And then it hands you this index into the file descriptor table as the file descriptor. It's called file descriptor in Linux. It's actually a file descriptor index because it indexes into the file descriptor table. And it's exactly a capability in that sense, right? It points to kernel internal data structures that contains those two things, the object reference, which is the pointer to the inode, and the access rights. And exactly the same thing is what seL4 capabilities are. They're similarly protected, they're kernel objects. All you get to see at user level is a pointer to them, like the Linux file descriptor, which is really the index in the file descriptor table. And then the kernel can look up the object and what rights you have and can check whether you're permitted to perform this operation on that capability. Okay? So that should give you a basic working understanding of capabilities. Why do we use capabilities? I'll get into that later in detail when I talk about this in the security lecture about different access control models. But fundamentally, there is the what's called access control lists, which is what you're used to in Linux and Windows and Mac OS, like the mode bits, etc., that control accesses to files. And then capabilities are the opposite one, the dual, if you like. And the advantage of capabilities is their fine-grained access control because they have object granularity, which you don't get with an access control list. So they're really the right mechanisms to implement what's called the principle of least authority, where any agent in the system, any process is only given as much as authorities actually as it needs to do its job and not more. And you can do that with capabilities. You can't do it with access control lists. That's why every serious security-oriented design uses capabilities these days. And for our purpose, in particular, they allow formal reasoning about information flow. That's how we can prove whether data can flow to certain subjects in a system, which is sort of the sort of stuff Scott is working on for timing channels, which I'll get to later. So in seL4, as I said, capabilities are kernel objects, so think of file descriptor tables. And in seL4, the equivalent for the capabilities are called C spaces. So every process, even though process is not an abstraction seL4, we have address space and threads. But the combination of address space, threads, and capability space basically gives you a process concept. And so the protection domain of a process, meaning its sum of access rights, is represented by capability space. And the capability space is basically a tree on it's a data structure containing C nodes, and C nodes basically array of capability slots. So a C node is like a file descriptor table, a list of an array of slots in which you can put capabilities, and they can be linked up. And the user can only have a reference to one of these C space slots, not direct access to capabilities. And they are linked by what's called C pointers. And the rights capabilities provide, there's only 5 of them. Read, write, execute, the standard stuff. Grant, reply, which is an unfortunate name. It should be called the call write, which is the right to invoke a server and get a reply back. And the grant write, which is the right to pass on capabilities. One of my other, oh, Andy, you've been here before, right? Yeah. And it's possible to derive capabilities from each other. If you have a capability, you can derive a new capability with the same or lesser access rights, and that's how you can have restricted propagation of access rights. For example, if I have a read-write capability to an object, I can derive a read-only capability and hand that on. And then I keep control over who can read the object, but no one else can write it, for example. So these are the basic concepts. And this is probably a good time to do the break, because the next thing is starting to look at the actual mechanisms. Any questions up to here? Yep. All right. We'll see you back in 3:05. Welcome back. So we had a look at a very high-level look at the principles and mechanisms in seL4, and besides the general principle, the one was capability-based access control, and I explained capabilities. And now I'm going to go through all the actual mechanisms, and today I'm going to cover the basic communication and synchronization mechanisms, which is IPC and notifications, and then the rest of them I'll do on Thursday. So, jumping right in, the most fundamental important thing in seL4, the mechanism you use all the time, is the protected procedure call. And it's historically called IPC, and it's too late to get rid of the term. It's actually misleading because, for reasons I'll explain later, think of what's short abbreviated as IPC as a protected procedure call, a remote procedure call, if you like, as you may have seen it in networking. So this is the really core operation you need in a microkernel because it's the way to go through these isolation boundaries, right? What the kernel does is isolate components, and then you need to have a way of communicating between those components, and the typical way of doing that is a client-server interaction. So the equivalent to a syscall in Linux would be this executing a function in a server, and that's called the IPC. So, and that allows the kernel to just focus on providing basic mechanisms and no services at all, because the services can then be implemented at user level. And what's the basic seL4 concept that, or mechanism that enables that, is the endpoint. So an endpoint is a rendezvous point where communication happens. So it's really the transfer point from a client to a server when the client invokes the server. I keep repeating, think of this as a function call. The client calls a function in the server. It just happens to be a function in different addressing and protection context rather than just a piece of its own code. And IPC and endpoints are the mechanisms that enable that. So what the IPC does is, as I said, it invokes a function, so it passes arguments along, and it returns a return value back to the caller. And that's done with this IPC mechanism through these endpoints. So in order to do this protected procedure call, the client invokes an endpoint capability, and as parameter passes arguments along that can get then delivered to the function that executes in the server context, and the server then returns. And the arguments, they are delivered by single copy, by basically the kernel directly passing them from the client to the server, from the caller to the callee. And so there's no buffering or anything involved. If you know other IPC mechanisms, for example, in System 5 IPC in Linux, they have these buffers where data gets put into by the kernel, and then when the receiver picks it up, it's copied back. You have two copies that way. This is just copying function arguments once. And that means inherently this is a synchronized operation. The client and the server need to meet each other at the right point. So logically, what happens is the client has a server capability, and it invokes this method on the server capability, passing arguments, and the kernel hands these across to the IPC, passes these arguments to the server function, and that then can reply back. So if you ever dealt with IPC before, forget pretty much everything you learned. In particular, so Linux kind of IPC, because seL4 is not a general purpose message passing mechanism. It's not a mechanism for shipping bulk data or anything like that. It's a mechanism for invoking functions in a different address and protection context. And all it does pass is you look at it being function arguments and return values. So this is how it works. You have a server that is a thread executing in an address space with a protection domain defined by its C space, and it keeps executing, typically in a loop, and then it gets ready to handle the next request. So it does this reply-receive system call, which is basically saying, give me the next request. And the client executes and eventually gets to the point where it wants to invoke the server. So it does this call operation on the endpoint capability, and that means the kernel then switches context to the server, copies the arguments across, lets the server execute its code, and then eventually the server finishes the request and returns the result back to the client. And again, this is done by the kernel context switching from the server back to the client, delivering the result value as part of this process. So it's really, look at it as a function call. And the way these arguments are passed is by what's called message registers. They are virtual registers, I get to that. And as arguments, you can pass either capabilities or straight data. In your system, you will generally not have to deal with passing capabilities. This is what you really need for more dynamic systems where access rights get extended and removed, etc. And the rest is just data words. There may be cases where I need to pass some capabilities, but it's an exception. The total payload is way too big. Up to 128 words. If you think of that as a function call, you would never pass 128 words as arguments to a C function, right? That's a crazy thing to do. Think of it that way. So anyway, who tries to use all these words is doing something wrong. We should actually restrict it, but it's just happened to be the space that was left in the thread control blocks, and that's why it's that funny number. You should never need more than, I don't know, 16, maybe 32 words or something. That would be a big function argument list. Okay. So fundamentally, IPC involves two threads, a sender and a receiver. But the more logical view is actually you have a single thread that just switches the context. This is basically gets closer to the notion of a function call, right? You can think of it, the client running and then executing a function call in the server's context and returning. So if you like, this is completely synchronous control flow where the server really doesn't have its own activity. It just continues operating, executing the server thread. This is enabled by the scheduling context, which I will get to later. In principle, the two can be completely asynchronous, the client and the server. But in practice, this is how you will structure a system, that the server just operates only on behalf of the client. That's what the server is supposed to do, right? It operates on behalf of the client. And therefore is really synchronous with the client, synchronized with the client, and you have this function call-like control flow.
Sorry, is that top right blue arrow pointing the wrong direction?
No, this is meant to the server blocks on the endpoint trying to receive, right? And then here the client comes along, sends to the endpoint, and then it's blocked until the server gets back to do the reply. So I should explain it a bit better, but it makes sense I agree, it doesn't necessarily make sense if you just look at it that way.
So you'll have an endpoint per server, or you have an endpoint per client?
Good question. Well, given the client invokes the endpoint sort of represents the server for the client. And therefore, yes, you have typically an endpoint per server. So the server has this request endpoint where it receives. And I'll give you a bit more detail in the next couple slides on how this works. Okay. So what really then is an endpoint? In terms of the kernel internal data structure, what does it look like? What do you think?
Would it be a reference to a thread? Would it be a reference to a thread? So which thread do you run the kernel?
Well, it certainly has a reference to threads of sorts, because if the server here does its reply receive operation, which is wait for the next request to come in, then it needs to block on this endpoint. So somehow the endpoint needs to reference to this thread that's waiting on it. Yep, that's a very good observation. And in the end, that's really all an endpoint is. It's a queue of waiting threads. And the threads queued on an endpoint can be either senders or receivers, but never both at the same time. So you either have a queue of senders or a queue of receivers. And in a well-defined systems, it's typically, well, it depends a bit. So let's look at a specific case. We have a server here with multiple clients. The server has this request endpoint, and then there's different clients trying to obtain a service from the server. And in the kernel, these are represented by kernel objects, each of which is controlled by a capability, right? So the server has a thread control block that represents the server thread. The server may or may not have a capability to its own thread. It doesn't need to have it, but someone who manages that server will have to have the capability. The server definitely needs a capability to this endpoint object because that's what it needs to receive from the endpoint. And then we have clients who have thread control blocks and each need to hold a capability to this endpoint to be able to send to it. So this is represented by the key symbols here. Each client has a capability to the endpoint. Obviously, the server has a capability to the endpoint as well. I didn't represent that here because it's less material. So what happens then if a client comes along and is trying to send to the server and the server is not ready to receive, then the endpoint queues the client. So there is a pointer from the endpoint to this client that is now blocked trying to send on this endpoint, right? And then if the server doesn't get around to dealing with this and the next client comes along and tries to send to the same endpoint, then it also gets queued and it gets queued behind. Well, it's a bit more complicated because the queue is ordered by priorities of the clients. If they're all the same priority, then they get queued in, first out order. And so whoever invokes the endpoint first is the head of the queue, modular priorities. So if a sender comes along first, then it's a queue of senders. If a receiver comes along first, it's a queue of receivers. So it's important to notice that an endpoint doesn't have a sense of direction, right? Whether you send or receive from an endpoint depends on, well, have you got the capability to do that? Typically, clients have send capability on the endpoint. They actually need this grant reply capability, so that's a bit of complication I'm not getting into right now. But the server definitely needs a receive capability on the endpoint to be able to receive messages. Importantly, this means if you want to communicate, you need at least 2 endpoints. Because otherwise, if there was only one endpoint, then a client would trying to receive from the same endpoint it sends the messages to, it would pick up its own message or that of a different client, etc. So basically, the server will only listen on the endpoint, the clients will only send to the endpoint. And in order to get back, you need sort of a second endpoint. Important observation here, in a well-defined designed system, if everything is single core, you should actually never have this situation. Because the server should always be higher priority than the client. And that's probably not quite well motivated at the moment. We will hopefully see later on why this makes sense. But the basic rule is the server should always be higher priority than the client. If you have a system that's structured that way, then you obviously see that you can never get a queue of clients on a server endpoint because the server has higher priority and will always be able to get to the point where it wants to receive the next request before any client can get to the point of actually making a request. It can happen on multi-core. If the server and the clients run on different cores, then things are obviously not synchronized, and the server might be busy while the client is ready to try to receive, and then you get these client queues. Yeah. So, how do you do the reply then? The server is generally widely available, so in a way it publishes its endpoint. Or in practice, in a dynamic system, there will probably be a name server that gives you a reference to the server's endpoint on which which clients can make requests to. But then the server needs to be able to reply back to the same client. If the server is only executing short operations that are basically run to completion, then that's not a problem. It just takes a request and responds back. If the server has long-running operations, then this doesn't work, because then the client requests will overlap. And somehow the server needs to be able to respond back to the right client. How do you do that? How do we get an endpoint for the server to reply back to the client? Well, theoretically, we could ask the client on the first invocation to pass a reply endpoint along. So it has its own endpoint, and it sends that to the server, and it says, OK, when you're done, reply back to me on that endpoint. This would be possible. Endpoints are relatively cheap, but it would force a stateful design on the server. The server would always have to keep this session capability for the client in order to reply back. And that's a bad thing. So instead, we have a thing called a reply object, and I noticed them, and they're one of the 10 abstractions. And this is used for the kernel to create a one-off reply channel back to the client. So by the server not only publishes its request endpoint, but it also, when it does the reply and wait, basically waiting for the next request operation, it provides to the kernel the capability to this reply object, and the kernel then uses that to create the channel by which the server can reply back to the client. So this is how it works. For the communication, the server has two things. It's got the endpoint and the reply object. The client has a capability to the endpoint, and the server has a capability to the endpoint as well as to the reply object. The client doesn't know anything about the reply object. And so the client, the server first blocks on the endpoint, so that's the normal operation. It's ready to operate on behalf of the client. And then the client comes along, invokes the endpoint, sends, and that means the kernel now context switches. It delivers the arguments to the server, but also blocks the client on the reply object. So this is basically as if the client immediately then switched to waiting on this reply object, except it doesn't know this reply object. All it knows is it performed this call operation on the endpoint. But the reply object was provided by the server, and the kernel now blocks the client on the reply object. So the reply object is also an endpoint, if you like, but with a few special properties. So it's different from a normal endpoint. And so the kernel delivers the arguments to the server, blocks the client on the reply object, and then the server can execute, do the processing, and then when it's done and responds back to the client using this reply-receive operation, it invokes the reply object. So that means it sends the response back through this reply object, and that then has the kernel deliver the result to the client, unblocks it, and it keeps on executing, whereas now the server is blocked again on the endpoint. So that's the basic way of how client-server invocation works. Any questions?
How does the client know which reply object to sort of wait for?
Well, the client doesn't know anything about the reply object. That's the point, right? The reply object is totally transparent to the client. The client only knows about the endpoint it uses to invoke the server. It's the server that provides the reply object, and the kernel blocks the client as if it had done a receive on that reply object, but it doesn't see that. So in terms of the client, it's a straight function called semantics, right? I invoke a function and I wait for it to return. Other questions? Cool. So in terms of the server, these reply objects really support a notion of anonymous clients. The server doesn't have to know who the client are. And if it's a stateless server, then that's typically enough. It doesn't need to know who's invoking it. There's a question of resource accounting, etc. That's a separate story. And this is where scheduling context comes in. But in terms of the basic model, the server can treat the clients as anonymous, doesn't really need to distinguish them. As long as it's stateless, if it doesn't have to, once it has to retain state on behalf of clients, things become a bit more complicated. And this sort of also maybe gives a little step to explaining the priority rule I explained before, which is not enforced by the kernel. This is sort of a design rule you should be following. The server always being higher priority, then basically it deals with one client at a time because clients can only execute when the server is blocked, and you don't get queues building up, etc. But there's other advantages of why this should be, other reasons why this should be done. If the server executes longer running operations that may block the client before the server responds back to them, then the server needs multiple reply objects in order to keep those channels. Because once the server has replied through a reply object, all the state is gone. So you cannot, there's basically, remember the reply object is the temporary response channel by which the server can reply back to the client. And so it can only be associated with a single client, and therefore if you have multiple client operations interleaved on the server side, it needs multiple reply objects. But that typically only happens when you have a stateful server. And this is just repeating. Always call high and receive from low. So server higher priority than this client. For doing stateful servers, you need a little bit more, because in a stateful server, the server has to retain some client state, and that client state will include the reply object that allows it to get back to the client. So this diagram here is a bit oversimplified, because it should show multiple reply objects really that point to different client state. But then the question is, how does the server identify client state? Think of a file system. I/O operations are long running. A client comes along, does a read, for example, whether that's from a network socket or from a storage device. It takes some time for the data to arrive, and the server wants to keep operating and serving other clients. So that means somehow it has to store the state of this suspended client operation, right? For example, your file descriptors. It's a typical kind of this kind of client state, right? If this is a file server, then it will have its file descriptors, which caches inodes and the point where you've read up in the file, etc. So, and if in particular, if the server retains state beyond a single request, as happens in a file system, where every read in the POSIX model, sequential reads read sequential parts of a file, right? You read a certain number of bytes from a file, and then there's a marker that points to how far you've read, and next time you do a read, you keep on reading. That's state that needs to be kept in the server across invocations by the client. So in order to do that, the server needs to have a way of identifying clients. So it can associate individual clients with the state it holds on their behalf. if you had only things I told you so far, the server would have to provide multiple endpoints in order to achieve that. Which, as I said, is not particularly huge a deal because endpoints are fairly lightweight, but it's a massive complexity that you'd impose on the server. So there's a better mechanism, and that's called batched endpoints. So a endpoint capability can be associated with what's called a badge. You can think of stamping it. You have the basic endpoint capability, but the server does not hand the raw endpoint capability to clients. Whenever it hands the endpoint capability to the client, it puts a badge on that's specific to the client. And how this identification happened, that's sort of a high-level protocol issue. The kernel doesn't care. So we now have different kinds of capabilities, client capabilities to the same endpoint, differentiated by the badges. And I symbolize them by these colored triangles. So the blue client has a blue badged capability on the endpoint, and the orange client has an orange badged capability on the endpoint. And the server uses these badges to identify the client state. And importantly, when the client invokes the endpoint using such a badge capability, the kernel delivers that badge to the server. The seL4 speak, it unwraps the capability because you can think of the cap being having the badge wrapped up because the client can't actually see the badge. It's completely opaque. But when it gets invoked through an endpoint, the kernel extracts the badge and hands it to the server. And the server then can tag its client state with the capability, with the badge.
Is this server untrusted software? Like this is not part of the server. What I'm wondering is does our info flow account for these calls from blue and orange?
So,
each other?
okay, the kernel here makes no guarantee about the server keeping client states apart.
Cool. Yeah.
Yes. So in that sense, yes, if the clients are mutually distrusting, they would have to trust the server not to mess up their data. So when the client invokes the kernel, the endpoint, as I said, the kernel passes the badge along, and then the kernel passes the badge along, and the client can then look up the appropriate client state for the invoker and deal with it. And if the other client invokes it, does the same thing, etc. So this is basically the way you can have stateful server with just a single endpoint, and that's almost certainly what you'll be using for your operating system. The operating system is basically a server that serves multiple clients, and it's obviously stateful, and so needs to identify the state which is the state that belongs to the client that just invoked it. Okay. Questions? No? We're getting close to the end. Yep. Basically, just digging a little bit further into IPC mechanics, you really only need to partially deal with this. A lot of that is hidden away in convenience libraries. One thing is virtual registers. I already mentioned that before. The kernel has this notion of virtual registers which are used for passing these the arguments. So think of, if you call a C function, then typically the compiler will try to pack as much of the arguments in registers as possible, and then there's calling convention that say whether certain registers are used for argument passing or not, etc. We have the same model here, and they are virtual registers in the sense that they may or may not correspond to physical registers, and typically some do, and others are just mapped into a storage, what's called the IPC buffer. And in particular, the number of these virtual registers that actually map onto physical registers then depend on the hardware. 32-bit x86 hardware just uses a single register for argument passing, whereas all the other architectures we presently support use 4. I'm sure we could do more. This used to be a fairly big deal in the past. If you read the original L4 papers by Liedtke, he's gone through lengths to make sure he uses every last register as much as possible for passing arguments, etc. That was really sort of a necessity of the hardware in those days because registers were way cheaper to access than the cache. These days, with highly pipelined processors, cache accesses are basically one cycle, and so it doesn't really matter too much. So that's why we don't really optimize that much anymore. The details of this are hidden by a library, so you don't really need to care about that. And in the API, we have this MR notion, so that's message register 0, which is actually not the 0th word, which is a bit confusing. And so the way this works is, before I get to that, so we have the operations the IPC operations you can do, and there's two fundamental ones, call and reply receive. So call we've looked at, you invoke an endpoint, that's a server endpoint, and that context switches to the server and atomically blocks the client on the reply endpoint or reply object. And it's really important that this is atomic. Why? I've given you all the information you need for that. You may have got lost in the noise.
If it's interrupted, if this call is interrupted, then you lose the state of those variables being passed through, right?
You don't necessarily lose state, but you're on the right track. What would interrupt it? Yeah, it could be. You could be unlucky. And of course, we always have to assume you get unlucky. But it's actually much more mundane. Remember what I told you about priorities? Which was? The server should be at a higher priority than the client, right? So what does that mean if you do this call operation? You call the server that's at higher priority. As soon as you switch to it, it will preempt. And the client can never get to the point where it can actually wait to receive the reply from the server. So by the time the server gets ready, the client is not gets ready to reply. The client is not in a state to actually receive the reply. And the server would either then sort of have to wait and run the risk of the client actually never picking up the message, or we need to make this operation atomic. That's the reason it is, right? By having it atomic, the context switching plus blocking the client on the reply object, we guarantee to the server that the client is ready to receive unless someone killed it meanwhile. So the server then knows it can just reply back, no complications. The client is either blocked on the endpoint and gets the message, or it's the client's fault because it died or something, someone killed it or whatever. Okay? So that's a really important property. Otherwise, that would massively complicate system design. And then the other operation is the reply receive, which I've also noticed several times before. So this is the server-side operation, which is also both have in common that they combine a send and a receive phase. For the client, the call is send message, invoke the server, so send arguments to the server and wait for the result to come back. The server operation, reply and receive, is I finished this request from this previous request, send the result back, and now I'm going back to wait for the next call. It's also atomic. That's not so necessary from the pure functionality point of view. It's actually sort of important for real-time considerations. So basically, the server cannot be interrupted either in this or preempted either in doing the reply to the client. The invocation of the return object is non-blocking, meaning if the client is no longer waiting for some reason, then the message just gets dropped on the floor. The server doesn't want to care. It shouldn't be its business. And the only reason that could happen is because the client got killed in the meantime by someone having control over its TCP. And when the server replies on this, there's actually an argument missing, important one. The reply object needs to be given, right? It needs two capabilities. It replies on the reply object and then receives on its endpoint. And once the reply object has been invoked in a reply-receive operation, it basically gets reinitialized, so it's worthless after that. Can only be invoked once. And then when the next request comes in, the kernel will reinitialize this reply object with a new return channel to the new client. There's also one-way operations of this, a receive only or a reply only or a send only. And the send only is actually fairly useless. I do not see any reason why you would ever want to use that one. So if you think of using a send-only IPC, you're most likely doing something wrong. The receive-only is needed sometimes. This is when the server provides a blocking operation, so the client needs to block for a long time while, say, some I/O completes, etc., and the server gets back to waiting for the next request. So then it would need to. It doesn't have a reply to go back. It caches its reply object, and it just goes to the next receive to wait for the next client. And there's a non-blocking send, which, again, on its own, you should have no reason to use. Important, and this is part of this design for security, and in particular, reasoning about information flow in the system. Any point where an operation or a return code would reveal something that's not authorized explicitly by a capability, you get no information back. And this is one of the reasons why you don't want to mess with send-only IPC, because a send-only IPC, because it only requires a send write, it doesn't have a receive, it doesn't need a receive write, so it should not get any information back. And that means it can't return a success status. You don't know whether the send has been delivered. So stay away from it. In any way, yeah, you need complex error handling protocols if you want to use that. So this is basically IPC, the basic protected procedure call operations. Any questions to this point? The other mechanism I want to cover today is notifications. They are somewhat similar to IPC, but much simpler. So they're synchronization objects. So obviously, the normal IPC operation, as we just seen it, implies a synchronization, but you should not abuse it as a synchronization mechanism, because you keep thinking of IPC as invoking a remote function. So if you want to synchronize asynchronous activities, then that's done with notification objects, and they are sort of glorified semaphores. So it's a notification object you can logically think as an array of binary semaphores, and you can signal them and you can wait on them just as normal semaphores. The implementation is each of these reply objects contains a so-called data word, which is 64-bit on a 64-bit machine. And whatever bits are sent or semaphore bits are signaled in the signal operation gets set in that notification word. And if there's multiple ones sent before someone waits on them, then they get all together, so you lose information. Be careful about that. And the way these get sent is by using batch capabilities. So the batch capabilities is looked at as a bit pattern, and it's just ORed onto this data word. And so if you have multiple batch capabilities on the notification with overlapping 1 bits, then yeah, if several of them arrive before they get collected, you lose data. Typically, in most cases, it makes sense to just have a batch with a single bit set for notification, so they're all separate. But obviously, there's only 64 of them, I think. Maybe I think it's 64. So there's a limited space. Should be enough for your purposes, no problems, because you mostly need them for dealing with interrupts, etc. So the sender can notify a notification, or signal notification, and the receiver can wait on it, as in the standard seL4 call, or it can poll it. So waiting returns the full data word and clears it, whereas polling is just gives you the data word as is and doesn't block, doesn't change the data word. You probably should stay away from that version and just wait on signals. So the way these work is you have 2 asynchronous threads, and in this case, the signal only goes one way from the one thread to the other. Obviously, typically, you use these signals for example, in the same way you use semaphores by synchronizing, say, shared buffers, in which case you typically have both, one for signaling the one way and the other signaling the other way. In this case, we just show one. So the one thread, it just polls to see is anything there, and then maybe it does something with it or not. Keeps on executing. Eventually, it hasn't got anything more to do until it actually gets a signal. So it just waits until the semaphore gets signaled. And then the other side can signal, and depending on whether these capabilities, if these were the same capabilities and therefore the same batches, then the second would be a no-op unless the other side collects the data word in the meantime, right? Because they get ORed onto each other. And because whether you can wait on a signal depends simply whether you have a receive capability on that notification object. So again, there can be multiple threads waiting on the same signal. And this is where you have, for example, if you have a multi-threaded server with multiple worker threads, they may use that. And that means, of course, you queue them. And it looks very similar to an endpoint. The signal has this notification, which has its notification word. And if someone comes along and waits on the signal and the notification word is 0, then it gets queued just as you get queued when you wait on an endpoint where there's no one trying to send to it yet. And if another one comes along, it gets queued behind. And in this case, it's purely, no, it should be priority-based as well. I hope it is.
If you have multiple people waiting, everyone apart from the first person will receive a null word, since wait clears the word.
Yeah. And so they wait until a client comes along. But depending on how the priorities are, in this case, the signaler may be higher priority than the receiver, right? And that's typically what you use it for if you want to signal things back, right? The server is always higher priority than the client, but the server may want to have an asynchronous protocol with its clients as well, and it could use signals for that. Or as I said, you could have a multi-threaded asynchronous server where the worker threads just pick things up from a signal. Okay, so now there's one complication scenario, and this is, think of a file server. So file server typically has 2 interfaces. A client interface, which is synchronous. So this is just a function call like open, close, read, write. And a actual device interface, an interface to the device driver, which is asynchronous because the device is asynchronous. So The client comes along, issues a read request. The file server issues the read request to the device, and then it needs to block the client and go back and wait for the next request to come in. And eventually, the device drive will signal completion of the I/O, and then the server needs to operate again. So the file server now needs to wait on two things. It needs to wait on the client as well as the device driver. With the mechanisms I've shown you so far, how would you do that?
Notification block also notifies the server when there is someone waiting at the endpoint.
So who does that?
I'm going to guess, I'd say the kernel will have to do that.
Well, either the kernel does it, but I haven't given you a mechanism by which the kernel would do that. So at the moment, the only way you can do that is having two threads. One listens on the endpoint and one waits on the notification, right? So this would force a multi-threaded design on the file server, which is bad. That's enforcing policy. So we should avoid that. We should not force policy like being multi-threaded. So to avoid that, and actually avoid complexity, because this multi-threaded design obviously would have a lot of gratuitous complexity, we have a way to have just a single thread that can wait on both an endpoint and a notification. And that's called notification binding. So we can say the notification gets bound to that thread. And that means if a notification arrives and the thread is waiting on an endpoint, the notification will be delivered to the waiting thread as if it had come through the endpoint. So basically, the signal is delivered logically through the endpoint. It's a bit of a complication, because how does the server thread know that what it's just received was a notification from the driver versus a request from the client? How does it do that?
Badges? Using badges?
Yeah, you're spot on. Using badges. So the client would get a badge, and the notification would have a badge, and obviously they're different, right? So the typical way you do that then is you divide the badge space by having the top most significant bit, say, of the badge space indicate whether that's a endpoint badge or a notification, and then you can use the notification bits to distinguish between different notification, and the rest of the badge to distinguish between different clients. So that's important operation here. And the rest is just simple mechanics on how these IPC messages work. You don't really need to worry about this. So the kernel describes a structure on the first word of an IPC message to distinguish whether you send capabilities or data or both, and tells you on the receive whether capabilities have been unwrapped, etc. So this is all encoded in this message format, which basically what that means is part of the message format is prescribed by the kernel and the rest is free to use for the user. And again, this is hidden in libraries, so you don't really need to care much about that. And just last thing is an example of how this gets used. So this is a typical use case. The client has its message info, and it has some convenience function for setting these registers. So in this case, the first message register gets set to a value, and then it invokes the call on the server capability. So that's the endpoint capability. And on the server side, it looks a little bit more complicated. There is some data structures allocate a slot in the for your in the C space, read types, untyped onto a reply object type. So this is how you get a reply object. There's this C-space management library we give to you so you don't shoot yourself into the foot too easily. And then it creates a derived capability. So it has this endpoint capability. It applies a badge to it to produce a new badge capability, which you then can hand out to the client. And then we assume there is some protocol where this gets handed out to the client. And then when the server gets to do actual work, it has a receive operation on the endpoint, which receives the badge of the client and provides a reply object for setting up the reply channel. And then when the server gets back to replying back to the client, it again sets up the message using this message info helper function, and then does a send on this reply object with a return value. So this is just boilerplate code, if you like. Obviously, this is bad style compared to everything I told you, because I always told you use call and reply wait and not send only and receive only IPC. So this is just for clarity to distinguish the two cases. What you really should be using is a server loop like that, which uses reply and receive. Obviously, there's some initialization needed. At the very beginning, the server typically doesn't have something to reply to, so there may be a simple wait receive to start with. But once the server is set up, it always goes through this loop, receive a request and reply to it and wait for the next one. And this is done by this simple reply receive. It's got the same argument as the sum of the previous one. So it receives from an endpoint, sends back the response. Somehow I think an argument is missing here. Hey? Oh, that's the reply object we're responding to, right? Yeah, okay. So it responds to the reply object with the response value, waits on the endpoint, and receives the badge of the next incoming request. So the send and receive get mangled into a single operation, which is more efficient and has some other advantages. And this is, as far as I was trying to get today, running 2 minutes over, but I've finished 3 minutes early the first hour. Any questions here?
Just a course logistics question. I read through the project you're going to receive receive access to the Odroid boards this week.
Yeah, we used to hand out these Odroid boards physically, so students could take them home. 2 years ago, with the pandemic, we were forced to have everything remote, obviously, so we set up a big battery of Odroids, and we're staying with that way because it's easier to manage. So you don't have to hand out kits anymore. There's a system where you can basically allocate yourself an Odroid in our cluster, and you can play with that at your heart's delight. And the details will be released. They should already be on the website, I believe. Any other questions?
Is that access like fully remote? We can do it from home, or do we need to be in the lab here?
You can do it from anywhere.
Awesome.
But you will get 24-hour access to a lab, and experience says make use of that. Part of that, I mean, we intentionally don't spoon feed you in this course, right? We throw it at you, maybe not quite at the deep end, but sort of somewhere in the middle. And so you need to do some of the swimming yourself. And it's very valuable to talk to your peers. So communicating in the lab about sort of how to do things or on the forum is highly recommended. And students find the lab experience very useful. Okay, see you on Thursday.